Okay, continuing with our previous discussion on the quantum theory of paramagnetism, we reached to the equation 9.44 shown here, which is the total angular momentum capital J as a sum of the angular momenta, orbital angular momenta total L, and the total spin momenta capital S. So let's move forward. The angular momenta L and S interact. Now this is the point, that the angular momenta L and S interact with each other via the spin-orbit interaction. Now this complicates the situation a little bit. Had it been not like this, then this would have been a simple algebraic sum. But now this is the vector sum. Not only that vector sum, but there are so many other concepts. So this interaction, spin-orbit interaction, is to be understood very carefully. This interaction exists above and beyond the Coulomb interaction between the electrons and the nucleus, and the interaction between the electrons themselves. Because of this interaction, the vector L and S are no longer constants. But the total angular momentum capital J remains constant. Now, this requirement, as shown in the figure, induces what is known as the precessional motion. So if we want to keep J constant and L and S are not constants, they are varying, and there is rotation as well. So that can only be possible if L and S are in precessional motion around J. So this is what exactly happens. So this precessional motion of the total angular momentum, but on the other hand, the dipole moment mu L due to the orbital motion, which is equal to minus E over 2m into capital L, and the dipole moment, the spin dipole moment mu S is equal to minus E over m into S, as we know that the gyromagnetic ratio for spin motion is double than the gyromagnetic ratio of the orbital motion. So this total angular momentum, represented as mu over here, and the total angular momentum represented by mu L, the orbital angular momentum, and the spin angular momentum. There are 2 points to be noted here. One is that the total angular momentum mu is not in line with the total angular momentum J. It is bit tilted at an angle theta, and this is because of the difference of gyromagnetic ratio between the spin motion and the orbital motion. And the other thing is that mu S and mu L are also varying, but mu is constant. So again there is a precessional motion of mu S and mu L around mu. So you must note that the total moment mu is equal to mu L plus mu S is not collinear with J, as in the pure moments mu L and mu S, but is tilted towards the spin because of its larger gyromagnetic ratio. The vector mu makes an angle theta with J, and this moment also precesses around J. Since the precessional frequency is usually quite high, only the component of mu along J is to be observed. So the component which is collinear, the component of mu which is collinear with the total angular momentum J is to be observed. The other component average out to be 0. So one can show very easily that mu average is equal to mu cos theta, and this comes out as the G factor, Landé factor, into minus E over 2m into capital J, where the Landé factor is given by equation 9.45. And this can be understood from any book on atomic physics. So this G factor, which we have used previously for a pure orbital motion, we must have S is equal to 0 and then J is equal to L, and G comes out to be 1, while for a pure spin motion L is equal to 0, and now J is equal to S and G is equal to 2. So these values agree with the discussion in section 9.2. Note that mu we used earlier in this section is equal to mu average, where the subscript is dropped. Okay, now this complication of the mu, mu S, mu J, capital L, capital S. What should be the values of these parameters for a given situation, for the electron, for which electron lying in which orbit? Now that should be understood. Now that was taken up by Hund's. He gave us Hund's rules, which are the best explanation to find the values of these parameters in different situations. So our question is, how may we determine L, J and S for the whole atom if all we know is the number of electrons in the incomplete shell and the angular momentum of this shell? So we do this by the following Hund's rules. The first rule is that the spin number S takes its maximum value allowed by the exclusion principle. The second rule is then L also takes its maximum value allowed by the same principle consistent with the rule 1. And the third rule is, if the shell is less than half full, then J must be equal to L minus S absolute, and if the shell is more than half full, then J must be taken as L plus S. So these rules were formulated by Hund's to guide us to find these values in a given situation for an atom. So let us explain and apply these rules, say, to carbon atom. Now we know that there are only 2 electrons in the 2p subshell, which can accommodate a maximum of 6 electrons. Now, these 2 electrons are unpaired, so one lies in, say, px and the other lies in py, and pz is empty. So this is the configuration, electronic configuration for the carbon atom. The rest of the carbon electrons are paired up in the lower shells. So as we know that for the paired orbitals and paired electrons, the magnetism is 0. So we will have to evaluate the magnetism due to these 2 unpaired electrons. To determine the angular momentum, we can take the 2 spins parallel to each other. This is to follow the exclusion principle without violating the exclusion principle, resulting in S is equal to 2 into S, which is 2 into half. So the value of S comes out to be 1, because each electron has spin half and they are parallel, so that's why the total spin comes out to be 1 for the 2 electrons. So this we have written following Hund's rule 1. Coming to the Hund's rule 2, to find the maximum value of L, then consistent with the exclusion principle, then L comes out to be 1. Why? This I have written on the side, since L is equal to 1 and ML is equal to 1, 0, minus 1. So only first 2 levels are filled with the 2 electrons. So that's why we get L is equal to 1. Since the shell is less than half full, because in P subshell there can be 6 electrons and we have only 2 electrons, so that's why the shell is less than half full, and we should use J is equal to L minus S absolute, and this comes out to be 0. Thus, in the ground state, the carbon atom has 0 magnetic moment. And that's why it exhibits no paramagnetism. So you see, even having 2 parallel electrons with parallel spin, the magnetism is coming out 0 to be 0 using the Hund's rules. In most cases, okay, so this is how we complete our discussion on the quantum theory of paramagnetism along with an example of carbon. But you must also go through the next 2 examples, one including rare earth ions and the other the ion group ions. So you must go through these pages to understand the paramagnetism of these two categories of atoms. Both these two categories show the paramagnetism, and you must go through this. Okay. So let me stop here, and I would also suggest you as a homework to go through pages 439 to pages 444 and to understand the remaining concepts of the paramagnetism and the spin paramagnetism, magnetism in metals, diamagnetism, etc. Although we have already studied the basic theory of diamagnetism and paramagnetism, both classical and quantum mechanical. So we have completed our discussion on diamagnetism and paramagnetism. Now we will move on to the third category of ferromagnetism in our next lecture. Okay, thank you very much.